Hello, everyone. Welcome to my talk, where I'll be talking about kind of how to use DVC, which is an open source tool, in the context of image segmentation projects. But the things that I want to highlight in this presentation I think will be applicable and relevant basically to any deep learning project. And specifically, I'm talking about like deep learning because we typically deal with like large data sets and long training times, right? And also large models, kind of binary artifacts that eventually result at the end of training. My plan for today is to do like a fairly quick presentation. Maybe like we'll wrap it up within 20 minutes, and then the rest of it is I have a live demo prepared. So as an example project that we got here is segmentation of pools from satellite imagery. And I got curious in this problem for two reasons. Like I have a little bit of background working with satellite imagery, more on the kind of raw data processing side, kind of applying image processing algorithms such as like orthorectification, image registration, and this type of stuff. But I also have a bit of experience in like computer vision on satellite imagery. And the second reason is like what you see up on the screen. It's kind of a very real application of this type of models on the government level. So French government, as of like, the article itself is from October 2021, but I believe they started using this system like much earlier than that. And the idea is they basically take satellite imagery, apply this model to it on a large scale, and try to identify which houses don't have pools registered in their like municipal database. And they can also estimate its area. And based on that, if there's a pool that doesn't match with their official records, they issue fines. And like I've linked to the article at the bottom, but I think they racked in like tens of millions of euros by doing that. So I don't know how much they spent on the project itself, but the ROI there could be pretty significant. So to start off, let's kind of put ourselves in this like mental space where I think we all commonly find ourselves, where we do have a Jupyter notebook that does kind of almost all of the stuff that we want, right? It does like data loading, data preprocessing, it trains our model, and finally we do model evaluation. If you have like at least a year of experience in like data science, at least, like, you know that at this point, like you're definitely not done, like you're not even close, right? There's a ton more stuff that needs to be done. But at this point, like you start asking yourself some questions, and some of those questions may be like, can you easily reproduce the results that you tried in the past and reproduce a very particular model? And if you tried many different combinations of like maybe algorithms or sets of different hyperparameters, are you able to kind of compare them sort of apples to apples in terms of their metrics? And if you want to go back to a particular experiment that you tried, will you be able to reproduce that in full later on? And oftentimes, if your work up to that point all was done in a Jupyter notebook, the answer is that you probably cannot reproduce an experiment that you did earlier, unless it was like the exact same day. But if the experiment, like if you did that experiment like a week ago, then a lot of things may have changed between now and then. And we ask those questions typically because we want to achieve certain goals. And I want to present like 3 goals that I think are fairly common when it comes to like computer vision projects and more generally deep learning projects. So we obviously want to achieve best performance. What it means in practice is we need to run many different experiments. And within the context of this entire talk, when I say an experiment, what I really mean is a very particular combination of code, data, and configurations. So it's not just like an experiment, meaning like a set of hyperparameters. And kind of, I mean it more in the global sense. A second goal is we do want to achieve reproducibility. And there are three reasons for that that I can see. Is first one is improving model performance, and because you cannot really improve things that you cannot reproduce, right? The second thing is transparency and collaboration. So you want your team members to know what you did in order to achieve certain performance. And the third point kind of may or may not be applicable depending on the industry that you work in and your company works in, but that's auditability. That is oftentimes required by laws and regulations. It obviously depends on your jurisdiction and the industry, but typically what that means is you need to be able to explain what exactly, and the emphasis here is on the word exactly, went into the model that prescribes, for example, like treatments to patients, or determines whether a particular customer can be issued a credit at a bank, right? Because you cannot simply like blindly issue treatments or just deny credit to a bank, to an applicant at a bank, and just say like, well, our model said so, right? That's just not good enough for many use cases. And the final goal is we do want to minimize setup and dependency on third-party services. And that is relevant kind of in many stages of your project. You could be an individual machine learning engineer or data scientist just getting started with machine learning experimentation. So you don't obviously don't want to spend a lot of time kind of setting things into place. Even if you work at a large enterprise, questions of kind of vendor lock-in, maintenance and cost and security concerns all come up very frequently. And for machine learning frameworks, what it often means is that you may not be sending like the actual company data into like a third-party service database, but you would still end up like sending metrics that are like metadata about like your training process, and that may still not be okay from a security point of view. So to kind of summarize all these three goals is that it's difficult to achieve all of them at the same time. That is, it's oftentimes difficult to iterate quickly and at the same time automatically track all the changes that you make to code, configs, and data, and also avoid this like dependency on third-party services to store your data and all the like metadata such as metrics and parameters. So here you can see in like a screenshot example of an experiment tracking framework, which is weights and biases. I took them as an example, and like don't interpret that as like me picking on them specifically, but this is like a common scenario across different frameworks that I tried, is that you may have very different metrics across multiple experiments. As you can see here, like F1 score ranges from like 24% to like 61% almost. But if you look at like a small subset of hyperparameters that I'm presenting, they're all identical, like the max depth of decision trees and number of estimators. And the problem that I see there is that in many machine learning frameworks, like experiment tracking frameworks, you have to explicitly tell them things that you want to track. And unless you track those things, everything else becomes like automatically, it's not tracked. So if you change something that is not tracked, then you cannot reproduce that later on. So, and that's kind of a problem. So my point here for kind of this talk today is that I do want to focus on open source. For a few reasons, is that it's easy to get started because you get community support when you encounter any problems or have questions. Typically these days when people talk about open source, it's automatically assumed that there's a project on GitHub. It's not always the case, but for in many cases, that is the case, that you would go and create like a GitHub issue with a question or a problem that you're experiencing. It oftentimes means that it requires like very little cost or like zero cost to get started. And you do get insight into like a public roadmap and discussions that happen around the tool, so you can like plan accordingly. And the specific combination of open source tools that I'm presenting today is Git, which I think and hope everyone that's currently in the audience is familiar with. We also got VS Code, which is an IDE that's becoming like increasingly more popular in the last several years. I myself made a switch from PyCharm to VS Code like about 2 years ago. And finally, DVC. So we'll use DVC to create machine learning pipelines. And they come with lots of additional benefits, as we'll see later on in practice. And they will help us achieve all the 3 goals that I mentioned earlier. So we'll be able to version codes and configs in Git, while our data set and models and other artifacts will be versioned in DVC remote storage. We'll use VS Code as a convenient user interface for experiment management. And as we'll see, there is no need to maintain or pay for additional services or infrastructure. So in short, what is DVC? So first of all, it's a command line tool. It has 3 core sets of features. It started out as a tool primarily for data versioning, and then later on expanded into machine learning pipelines and experiment management. And those 2 other sets of features come with kind of integrated and automated like data versioning. And I can elaborate what that means during the live demo. It is open source, and it was by design, it integrates very tightly with Git. And it's language, platform, and storage agnostic, meaning that, like for example, during today's live demo, I'll be using a Python-based project, but it doesn't have to be. You can use whatever language you prefer. I even know people who use it with like proprietary platforms and languages. I know if you use like MATLAB, you could totally use DVC and build like DVC pipelines from MATLAB scripts, for example. You can use it on Windows, Linux, and Mac, and pretty much any type of storage you can think of is supported, like obviously cloud buckets, and then network attached storage, SFTP, SSH, all of that stuff. So what are DVC pipelines? So let's start with like a concept of general like machine learning pipelines. It's the idea that you would break up kind of logic of sections of code that are kind of self-contained and logically should like follow one another and depend on each other's output. So you'd kind of isolate them and create essentially connected stages, stages that are connected with each other by inputs and outputs. So with DVC pipelines, you can create a pipeline based on like a series of scripts, whether it's like, as I mentioned, Python scripts, R scripts, or any other language. Or if you wanted to, you could still do most of your work in Jupyter and still leverage the like data versioning benefits of Jupyter notebooks. And here's what I mean, kind of for the 2 use cases is on the left-hand side, we see how you would define DVC pipeline in a YAML file based on a series of Python scripts. There are 3 stages. Each stage has a command that needs to be executed from your like terminal. Like you can see Python process data, Python train.py and eval.py. And then the rest of it in every stage is just defining what each stage depends on, so it can track the changes. What it generates, whether it's an entire directory or individual file, and outputs of one stage can be inputs to any other number of stages. On the right-hand side, If you prefer to stick to the notebook to do most of your like exploration model training, you can run that notebook through a DVC pipeline with the help of Papermill. So Papermill is another open source project. It was released by Netflix a few years ago. It allows you to execute your notebooks from command line interface while still being able to provide parameters into the notebook. So Papermill is a really cool tool on its own, even though it's not a focus of my talk today. But the point is, once you define your pipeline in whatever kind of flavor you prefer, you'll be able to start executing those pipelines with some customized set of hyperparameters. For example, you can just say like DVC X run, so experiment run with number of estimators, whatever, set to, I don't know, a new parameter, and then DVC will figure out like which specific stages it needs to run to execute that experiment, and then you can do so like as many times as you want. You can either change your code on individual hyperparameters and keep running those experiments, and eventually, with the help of a VS Code extension for DVC, you'll be able to see kind of a table of all the experiments that you've tried, all the different sets of hyperparameters that you've tried, and compare their performance metrics. Here, this is going to be the project that I'll showcase today. As I did the intro like in the beginning, we're going to train an image segmentation model with DVC pipeline. And I have this project opened up and cloned in my browser here. So what you see is VS Code running in the browser. And the first thing that I should mention is that when you don't have DVC initialized in your project, it's fairly easy to get started with data versioning. So the first thing that you would do is you would do like pip install DVC. So it's as easy as that. If you want to use like a specific type of remote storage, for example, if you use AWS S3 buckets, there's an S3 extra that you can add, and it will install additional dependencies like Bottle3 and all that stuff. So I already did that. So I have DVC installed on my machine. And the second thing that you'll need to do is do DVC init. And you can see that this command is like very similar to how you would get started with Git in a project where Git was not initialized previously. And when you run this command, it will create this .dvc directory. And inside of this directory, one of the most important files is this config. And this config, you can specify one or more what's called DVC remotes. So you basically specify the location of your remote data storage. In my case, it's an S3 bucket. So I created an S3 bucket and configured my access to it on this machine. And when you do that, you can start versioning your data with it. So for example, I had my data directory living in this data directory. We can see that in the Git repository itself, there's no data directory called like pool data. There's only this .dvc file. And what happens is, let me first do DVC pool to kind of show you what happens when you start versioning files or directories with DVC. So I just did DVC pool, and this pool's data directory appeared in my local workspace. And initially, when I wasn't tracking this directory with DVC, what I had to do is do DVC add data and then point it to this directory. And when I did that, this .dvc file was created. This is a kind of a pointer or reference file, if you wish, to the original data set. And at the same time, in the git ignore file, DVC adds the name of the actual directory. So these are kind of the two things that happen. Git starts ignoring that directory while DVC creates the reference file. And then you can push that data into your remote, in my case, S3 bucket. Yeah, and that's pretty much it if you wanted to get started with just data versioning with DVC. Then, as I mentioned, this is only one subset of features that DVC has. The second one has to do with pipelines. So imagine you have a notebook where you do most of your kind of data pre-processing and training. I do have that in this repository that I'm showing. It's fairly concise and short, but that's already kind of enough code that it starts kind of being like very hard to manage. And there's like just kind of loading the data, splitting into training and test. There's like processing mask files, because this data set comes with satellite tiles of satellite imagery, and then masks. So these masks, like when you visualize them in like an image viewer, they're all black because the pixels here are 0 and 1. And what the image viewers are used to is two images where the pixels are between 0 and 255. So basically, if you scale it, you would see the mask, but not in the image viewer. Right, so we've got this notebook. It does what we want. But then the problem right now is if we want the notebooks to be reproducible, we have to run them like end-to-end every single time. Otherwise, because Jupyter notebooks allow us to execute cells out of order, we sometimes kind of, it's hard to guarantee their reproducibility. So typically what we do as a first step, right, and that's even like putting DVC aside, what we oftentimes want to do is refactor our notebooks into some predefined and executable Python scripts. And here's exactly what I did with that notebook. I basically split it into 3 parts. One does data splitting. And you see by kind of these 2 lines here that I can run this script from command line. It's saying Python source data split. And then this would run like a data split script for me. And here we go, like with same stuff with model training. I can launch it from command line and evaluate. And you can see kind of there's nothing really DVC specific within this code. So let me undo some of the changes. So once we have our notebook refactored into individual scripts that I can execute from command line, that's when we're kind of in a good shape to start putting together our DVC pipeline. So you would define your pipeline in a YAML file, and that YAML file basically needs to have different stages defined in it. For example, here's the data split stage, and all the the structure of these stages is all like very similar. Every stage needs to have a command defined, like what you run if you want to execute that stage. The dependencies that this particular command depends on, it can be a directory or an individual file. And then there's a parameter section, which serves also like a dependency, but not on directories or files, but on values that you define in this like params.yaml file, right? Where you can control things like percentage split between train and test subsets, like random seed, and then like in this case I chose like that I wanted to tweak model architecture, image size, and like batches, the size of the batches that get fed into the training process, and all of that stuff. And then the output, like in this case, when I do data split, it actually takes the raw data from this full data directory and then splits based on like currently 15% of the data goes into the test data, and then the rest 85 go into the training data. So this script, when you run the script, it creates these 2 directories. And remember the asterisks in the slides that I've shown you that DVC pipelines come with like integrated data versioning. And that's exactly what I meant in this case, is that every output of the pipeline gets automatically versioned by DVC. So you see that these two directories are also part of the gitignore file. And when I run the pipeline and it produces those directories, all I have to do is run like DVC push to push those directories into a DVC remote. And then for the training script, it's all like very similar. We've got the command, we've got dependencies, got parameters, but the train stage outputs a model binary, like this pickle file, instead of a directory. So this is how you define a pipeline. Once you do that, you can start running your pipeline using the DVC experiment run command. So you can run your pipeline as is. So in my case, I ran that pipeline earlier, and right now I did not introduce any changes. And DVC is kind of smart enough to figure out that none of the state, like the data didn't change, none of the stages defined in the pipeline changed. So there's no point of like wasting computational cycles and rerunning the pipeline. But see what happens if I decide to change some hyperparameter. I know, let's change batch size, I know, from 8 to 10, right? So we can do this by saying DVC experiment run. And then this batch size parameter is nested under the train section. So we say train.batch size, and we can set it to like 10. And what happens right now is that DVC did detect that the data didn't change. And also we didn't change anything about data splits stage, so it skipped that. But batch size does affect the training stage of the pipeline, so it does rerun training right now. So I set the image size to be like fairly small, and also we're only training for 10 epochs, so it should be complete within like, I know, 10 to 15 seconds, sorry. Okay, we're running evaluate stage right now. And this is pretty much how easy it is to like run your first experiment. Like we just did that where we had a predefined pipeline. We wanted to change a hyperparameter, and we just did that. And when we want to, like, imagine you did that like 20 times. Now you want to compare your experiments. So what you could do is go into like this extension marketplace in VS Code. If you search for DVC, you'll be able to find this extension. I already have it installed. And here in this extension, you can see that you've got like, that you can first of all compare your experiments. So I've got like one that I ran before started, and the one that I ran with like batch size of 10. That's the one here. So I can see, let me zoom out a little bit. I can see the loss, and what I'm measuring is this dice metric, because it's a segmentation problem. So I can compare like multiple experiments using this. Maybe I have a hunch that, I don't know, by changing like something else, maybe a model architecture. So ShuffleNet is pretty small architecture, so we can try something else like ResNet, I know 18 at least. Let's try that. So we'll probably have to download the pre-trained model from PyTorch. Yeah, that's exactly what's happening right now. And we see that this new experiment is running, and we can show plots and kind of observe them as the metrics update in real time. We can see like fairly early on that the dice metric is in the first epochs is already has higher values than what we had with a ShuffleNet architecture. So that's a good sign. And now we're on the final epoch. we can compare, for example, this experiment, and we can see also here as part of my evaluate script. Let me show you this source. There's part of it where I basically select. There's a parameter that controls how many test images we want to run through the model and save those images with a mask overlaid. Where's that? So basically take, yeah, here. So n samples to save that lives in our parameters file, and we'll basically overlay those masks and save them. And we can compare those 10 images across different experiments that we run, right? This is just like a sanity check as we like change our hyperparameters. Let me close that. As we change our hyperparameters, how does the mask on the output change? And we can see that like with this ResNet architecture, we kind of get slightly better performance, which is a good thing, right? So let me move this dice metric over here, and I can sort them in, let's do in descending order. So I can see that I get like a significant improvement in this dice metric. So I've identified an experiment that performs better than all the other ones. What do I do next? So you've got like a few options. The option that I probably use the most is this apply to workspace. What it means is that DVC extension basically resets my local workspace, all the uncommitted changes to the state of that experiment, right? So I've got like batch size of 10. This is the ResNet 18 architecture. And at this point, I can just go ahead and say like try ResNet 18 and 8 and 10. And let's say batch size of 10. And I could simply commit that into my Git history. And the other thing that I would need to do is also push all the resulting artifacts into the remote storage. And there we go. I can now go back to my Git repo, and I see this commit that I just made. I can see all the details of this commit over here. These are the comparison images. These are the metrics, and everything else is in here. So basically, your entire experiment can now be self-contained in one commit, so you can return to it like at any point in time. And then, so everything that I've shown you at this point is entirely like free and open source. Both DVC and VS Code extension for DVC are both open source. But I can also show you that there's a free product called Studio, where it brings you some like additional benefits when it comes to like visualizing your experiments and sharing them with other people. So for example, I can make this view public, and maybe I can share that in the chat if I can find that. Yeah. Yeah, there you go. So everyone who can see the link in the chat should be able to kind of see the exact same view that I'm showing. So you see that this last experiment that I just tried and pushed that, it shows up here with the improved dice multimetric. I can select this experiment and the previous one and compare the plots. So I get kind of a very similar view as what I had in VS Code. But now this view is viewable potentially by my teammates. And one last thing, and a really cool feature that I want to show is the ability to view these experiments in real time. So what we'll do is, let's see if we can get an improvement by training for longer than just 10 epochs, right? So what we'll need to do here is, first of all, go into Studio and set our, so there's a Studio access token section, so we can copy that value. And I'm going to set that value studio token. And now if I do the exact same thing as I did before, so DVC experiment run, but now I want to do train.fine tune arguments and set number of epochs to, let's do 15, so that it trains for just 5 epochs longer. And now what I can see is that when I started this experiment, I can see this live experiment being trained. And now we're just on the first epoch, and the new values from the training process are going to start showing up in here. And the benefit here is, again, if you do deep learning, is your training typically takes like hours, right? In some cases, it may take days. And you don't want to waste computational cycles if you see that your loss function goes in kind of the wrong direction, or it plateaued earlier than you expected. It might make more sense to go and terminate that experiment. So by having an ability to view how your training progresses, basically from any device, anywhere, right? As long as you can like access this project view, you can go ahead and terminate the training process on like whatever machine that happens. And then imagine if that's experiment, so it's done now. If, like in my case, training for longer actually resulted like in a better metric, which is good. Basically, again, going to like where I trained it, I could go ahead and apply it to my workspace. I could even create like a whole new branch out of it if I wanted to. But the point is, like, if it's a good experiment, you can persist it in your Git history. If it's a failed experiment, not to worry, you can just delete it from your project view and it's gone. So you kind of have this good balance between iterating quickly and also at the same time not committing everything under the sun into your Git history and still keep it organized. So that's really it that I had for the last demo. And let me go into the summary slide. So I think with this combination of open source tool that I proposed here is we kind of address like a few pain points that are common with machine learning experimentation, and especially with deep learning problems such as image segmentation, is that we can generate a large number of experiments. We can version code, configs, and data all in one place. And even though it's not like a zero setup, we still had to do some setup, but I think it's almost like as minimal as it gets for us to be able to achieve kind of reproducible machine learning experimentation. So we used Git for versioning code and configs. We use DVC for creating machine learning pipelines and generating many different machine learning experiments. And because it came with kind of integrated data versioning, which is especially useful for large data sets and large models that we deal with in segmentation problems, right? Like in this case, the model that I generated is like a couple 100 megabytes, which definitely like is not something that I would recommend fitting into your like Git repo as is. And finally, we use VS Code as a convenient UI for visualizing and managing machine learning experiments.